Hi everyone. Today we are going to discuss about the EDFA amplifier, which is used in optical communication, and we will discuss about the 6 questions which are written here. Why amplification is needed in an optical communication network, and second is what are the optical characteristic of EDFA. Third question, we will discuss how EDFA works, the internal architecture of the EDFA, and what components we use in EDFA. And fourth one is the control mechanisms used in an EDFA. So, what are the how we control the gain and other parameters in an optical amplifier. How to plan an EDFA. After that means what are the different application of an EDFA in an optical network, and lastly we will see about the signal flow which is used in EDFA, how the signal comes from the fiber and how it flows on the other equipments through the internal diagram of the EDFA. This slides gives us answer about why amplifier and what amplifier does. So first of all, why amplifiers are needed? The answer is simple, because as per the characteristic of the fiber, when signal travel in a fiber, its amplitude and power get reduces. So to regain the power, we need optical amplifier to amplify the signal. As shown here, input power is low, so we are placing a optical amplifier. It is rising the power level through the uh, through the amplitude of the signal. Amplitude, you can see the amplitude term over here. Just a minute, I will tell you. You can see the amplitude of signal here is less, whereas the amplitude of this wave has been increased through the optical amplifier. So in this amplifier we use pump lasers, and the function of the amplifier is 1R. 1R means only the re-amplification. We have 2R function also, which is a re-amplify and a reshaping of the signal. It is done by an equalizer, whereas we have 3R of amplification as well. 3R of amplification is done by a regenerator. uh, it is basically a transponder where OEO functionality is happening, optical to electrical, and electrical to again optical. So the third R in 3R is your read timing of the signal. So it will reshape, retime, and re-amplify. But here in optical amplify, it is only 1R, which is the amplification. If we see the advantages of amplifier, it does all optical amplifier could be used as a signal regenerators, where a loss is limited. It uh, it is used in different ways in a network. One is to signal regenerate, to just amplify the signal. Whereas the other advantage is a signal amplifier could be used for amplifying multiple channels. So in wavelength division multiplexing, we know we have multiple channels, and that all can be amplified at once. So this is the basic characteristic of an optical amplifier, and also it amplifies independent of bit rate and modulation rate. Even a 10G signal and a 100G signal with QPSK or BPSK modulation can be modified at once. So if we see the specification of optical amplifier, first of all, the main thing is gain. As we know, the amplifier gives us a certain gain, like 15 dB, 20 dB. It is amplifying the signal as per the gain we are setting in the amplifier. So second one is optical bandwidth. Optical bandwidth, if we take any C band amplifier, its optical bandwidth is from 1530 to 1560, entire C band. And third one is gain flatness. So uh, the optical amplifier has relatively uh, good gain flatness. But in forward slide we will discuss about how we achieve the perfect gain flatness, means the same gain for all channels. Noise figure. So noise figure is also an important component, because noise is introduced in every amplifier. uh, so noise figure gives us the information how much noise is introduced by that amplifier. Noise figure is simply the signal to noise ratio at input of the amplifier, and once the noise is introduced through the amplifier, then we get the signal to noise ratio of output of the amplifier. So once we divide the input signal to noise ratio to the output of the signal to noise ratio, we will get the noise ratio of value. So this is particularly the formula. So maximum output power. Here we always try to achieve from an optical amplifier the maximum output power what we can launch in the fiber. So coupling loss of an amplifier should be minimum. So pumping efficiency. So pumping efficiency should be maximum. As the pumping efficiency increases, the gain of an amplifier increases. So pumping efficiency is directly proportional to the gain. Whereas the polarization dependence and crosstalk of an optical amplifier is minimum. So these are all parameters which we see while selecting an amplifier. Moving ahead. So this diagram tells us about when uh, we amplify a particular signal. So this is the start point of any signal. So as the distance of the fiber increases, or the signal increases in the fiber, it get attenuated. Once it reaches near to the RX sensitivity, so this is particular threshold of the receiver. So at this point we again increases our signal, uh, so that our signal won't go under a receiver sensitivity. Once the signal goes under the receiver sensitivity, it is not possible to recover signal again from that level, because the burr level is so high that we cannot segregate the noise and our actual signal. So for that we place an optical amplifier in the network so that our power level increases, even though the noise levels are also increases when we use any amplifier in the network. So that's why the amplifier could be placed between two sites are always limited. So let's move ahead. So this one is the optical amplifier diagram, specifically EDFA. Here we use two pump sources, 980 wavelength, a 980 nanometer wavelength and 1480 nanometer of wavelength pump laser source, and our this is our input signal. So through isolator we both the signal goes in the coupler. So coupler will combine both the signal or multiplex both the signal through the WDM technology, wavelength division multiplexing. The most important component of EDFA is the fiber. It is known as EDF fiber, Arabium doped fiber. So in this fiber we have Arabium doped fiber, Arabium ions doped in the fiber. So that ions particularly help us to transfer the pump laser power to our actual signal. So what we are doing in EDFA amplifier, we are transferring the pump power to the weak input signal, which is our channel in the case of WDM. So that is done with the help of EDF, and a narrowband filter is at last used because we want to reduce the out of band noise in a particular signal. So these are the component. We will discuss in detail what is the function of each component in further slides. So in this particular figure, we are discussing the detail input functionality of EDFA. So here we have three stages in an EDFA, or we can say the three energy levels in an EDFA, which is E1. E1 is known as ground state. This level is known as the excited state, which is E3, and the most important stage is E2. E2 is particularly known as metastable state. So once we pump in the pump laser, which is 980 nanometer approximately, the first step goes into the fiber. EDF fiber is stimulated absorption. So stimulated is something uh, we are contributing or helping the ions from the to helping the ions in the ground state to go into the excited state. So this functionality going the ions from the ground state to excited state through a pump laser is known as stimulated absorption. So they take the energy of the pump laser and go into the excited state. After going in excited state, it comes back to metastable stage, the level E2, who by themselves through fast decay. So in this stage, the ions will be there for a longer duration. So it's a relatively stable state as compared to the excited stage E3. So that's why it is known as metastable stage. So after coming to this stage, some ions will automatically emit some energy and comes in down again in the ground state. So that automatically emitting the energy is known as spontaneous emission. So this particular type of emission is the noise component in an amplifier. So spontaneous emission always happen. So it is a natural phenomenon, and that is a noise factor of an amplifier. So once the spontaneous emission photons come into the amplifier, this one let's suppose, and then what happen, it also get amplified with our actual laser signal. So that's why we call it ASC, amplified spontaneous emission. So noise also get amplified as the photons propagate in the fiber. So the last operation is our stimulated emission process. So once we uh, put the laser signal in the EDF Arabian doped fiber, and uh, the ions which are in metastable state with the help of stimulated absorption, that gives the energy to this weak laser signal through a process known as stimulated emission. In this process, the lasers will uh, provide the same photon as of our laser signal. So if we are putting a laser signal in a spectrum of C band, let's suppose 1520 to 1570 nanometer, then in stimulated emission the photons will give the coherent photon of this particular laser signal, and it get amplified, and that ions which are in metastable stage comes back to the ground state. So this particular process contributes in amplification of the signal. So I hope you understand this complex process, and it is a very important process for any EDFA amplifier. And on two factors, the efficiency of EDFA depends. One is our pump laser, as I told you the pump laser efficiency earlier, and second is the doping concentration of the EDF fiber. So the more the doping erbium ions, which are Er3 plus ions, present in the ground state, more amplification we will get in an EDFA. Moving ahead, this particular graph tells us about the gain and the noise figure combination. So here on the y-axis left side we have noise figure values, on the x-axis we have input power values, and on the right side y-axis we have gain values. So our EDFA can be designed in two types: counter pumped and co-pumped. So we can put the direction of the uh, pump laser in reverse. In case of reverse direction, it is known as counter pumped, and the which we saw earlier, this one is co-pumped, because the laser signal is also going from left to right, and our signal is also going from left to right, which we want to amplify. Uh, so moving ahead, so there are two types. The major difference between co-pumped and counter-pumped amplifier is that a co-pumped has a relatively uh, low noise figure, whereas counter-pumped has more gain efficiency as compared to co-pumped. So at particular noise level, as you can see, the input signal is always minimum. If we give input signal higher in an amplifier, let's suppose if we give -8, then the noise figure increases for both co-pumped and counter-pumped, and our gain decreases. Here we are getting the gain of minus 19, uh, this level, uh, the 19 dB. Whereas if we give the power -28, the weak signal, then our noise is relatively low. As we can see here, it is below 4 dB for co-pumped and below 6 dB for counter-pumped, and our gain levels are particularly high, which is more than 25 4 dB in case of -28 dBm power. So this is a basic phenomena. Always we try to give a low value of input power in an amplifier and transfer the pump energy efficiently to our input signal. If we give the high input signal, the efficiency of optical amplifier decreases. Moving ahead, yeah, this figure is tells us about the absorption and emission of a particular amplifier. So as we can see, if we give a 1480 nanometer pump laser, so absorption at this particular level is higher than our emission. So absorption means we are talking about the stimulated absorption. Whereas if we go to the C band, which is from 1530 to 1560, here uh, at this level you can see the emission, which is particularly from the metastable state to our ground state. The stimulated emission, that is higher as compared to the absorption cross section. So but here you can see the emission rate is not flat. We want equal amplification for all the wavelengths we have in C band from 1530 to 1560, but here the amplification or emission is not flat, and it relatively depends upon the wavelength. The bigger the wavelength number, the lower the energy is. So it is the basic phenomena and then uh, of physics, that the higher the wavelength you choose, it has less energy, and the lower wavelength you choose, it has more frequency and energy as compared to the higher wavelengths. So that's why the amplification, as we discussed earlier here, so as the input power increases, the amplification decreases. So same thing happens here. The 1560 wavelength has higher energy as compared to 1530, so the amplification of 1560 is less as compared to 1530. So how we counter that, or we get a flat response? As you can see, the our ideal target is to get this type of response for every wavelength, because we want to maintain the flat per channel power for entire C band from 1530 to 1560. How we will do that? First of all, we check the error which is coming in the output of an amplifier. So as you can see, this particular wavelength is error wavelength. So this is a natural response of an EDFA amplifier. So we design a particular type of filter which gives the reverse of this particular response. So what we do, uh, uh, we create a filter, dielectric filter, and put it at the input before going the signal to EDFA, this type. So it's this particular filter respond exact opposite to gives us exact opposite response to the EDFA response as shown here. So if we give the negative input to our amplifier, it will eventually give us a actual flat response at the output, because a negative and positive of same. So this is the amplifier response, and this is our error which the dielectric filter gives us. And once we subtract these two, we will get the actual flat response which we want. So this is one of the technique, optical filter used for flattening the gain response. The second technique is that we can make a certain type of amplifier, like we can dope aluminium we can do aluminium doping in EDFA. So that gives us relatively a, a more flattened response as compared to non-aluminium doped. As you can see in this figure here, the response is uh, just not that much flat, but with the help of aluminium doping and erbium doping in the EDFA, uh, we get a relatively flat response as compared to this. So these are the two techniques. There are number of more techniques to get the flat response, but here we are discussing these two only. Moving ahead, here we are discussing the EDFA gain control. So how we control the gain? So it is basically gain locking technology of controlling the pump light source. So here we are controlling the pump laser with the help of inputs we are getting from the output and input of an amplifier. So why it is important? Because in a multi-channel system, like if we have multiple channels here in the C band, so once some channel, like two channels goes down in particular fiber, then these two channels will get extra amplified, uh, because the ions and pumping laser is same here, and they transfer more energy to these two channels. So we don't want to do that in particular WDM system, because it will eventually harm your receiver, or because these overshoot channels are not in control, and they can damage your receiver transponder. And we want the gain to be at certain level, uh, so that we are controlling the system. So this is a particular control mechanism known as clamping also. So in this particular mechanism, what we do, we take the input reference power before going putting the signals in the pump laser, and we are controlling the pump with the help of uh, input power what we are getting here. And we also take some tab or some power from the output of that amplifier. So how much amplification has been done by this amplifier, we take the ratio and control our pump power accordingly. So once we get to know, oh, that two channels are down in an amplifier, so we are getting no power for first channel and second channel, we will reduce the pump power so that we can maintain the gain at the output level for the rest of the channels. So that is basically a control a loop phenomenon which we practice, or this is the circuitry we have in the amplifiers to control the gain lock. Yeah, this slide is particularly of application type on based on different amplifiers. So we can use an amplifier in the practical application by three ways. So first is your inline amplifier, which is shown here, and second as the power amplifier, which is also known as booster, and a third is your pre-amplifier. So this one. So here inline amplifier is basically used in the long hole system, in which we have periodical power boosting done by a series of amplifier. So here what we try to achieve, we are just uh, giving the gain of this amplifier as per our span loss. So span is particular distance from a point to b point. So this inline amplifier is accommodating the span loss of this fiber. So the same is done by the rest uh, of the amplifiers which are placed in series or cascade of this system. So that's how this is one of the application. So the other application here is the power amplifier. So power amplifier or booster we place at the transmission side. So this is particularly a single site where our transmission or transponder is there, which is generating the signal, and we are placing the booster on this amplifier before going to the receiver. So this configuration is known as power amplifier or amplification with the help of amplifier. So third type of amplification we are doing here is pre-amplification. So pre-amplification is done at the receiver end. So this is the side B, and the amplification is placed at the side B near to the receiver to accommodate the loss of the fiber or to increase the receiver sensitivity. So here the power amplifier or the booster is just increasing the transmitter power or transmitting power in an fiber, whereas the pre-amplifier is used for the improving the RX sensitivity of an signal. The first one, which is inline amplifier, it is used in long haul system where our distance is more than 500 kilometer or 1000 kilometer, and we require a number of amplifiers in series or cascade to transmit from site A or transmission site to the receiver side. Yeah, moving ahead. So these are the key parameters which we see in an amplifier, which is a typically internal gain, as we maximum internal gain. So we also always give the range of the gain in an amplifier, which could be from 20 dB to 40 dB, and insertion loss of that card. So insertion loss is basically the loss which is introduced by an electronic component. So this is between zero point 0.1 to 2 dB of an amplifier. So polarization sensitivity, we don't have. The EDFA amplifiers are not polarization dependent. So this is no. So pumping source is optical. We also always use an optical pumping source, as we discussed earlier, as 980 nanometer or 1480 nanometer wavelengths. Optical bandwidth. So optical bandwidth is could be entire C band, as we discussed earlier. It is from 1530 to 1570, 40 nanometer, or in some amplifier we also have C or C plus L bands, optical bandwidths. So they work for both C band and L band. So that is known as a C plus L band optical amplifier. So maximum output power, so this is an important component because how much a maximum output power an amplifier can give, and typically it is 23 dBm practically for an amplifier. So this is the noise figure as we discussed earlier. So it is 4 to 5 dB practically for an EDFA amplifier. So noise figure is nothing, it is the ratio of signal to noise ratio at the input of amplifier to the signal to noise ratio at the output of the amplifier. So once a signal passes through an amplifier, the 4 to 5 dB noise is introduced by every amplifier component. In this slide, we will discuss about the internal diagram of a bidirectional amplifier, how the signal flow works in an amplifier. So this is a particular card uh, which is used in an amplifier, which is used as an amplifier. So here you can see these are the components which are used. First is erbium doped fiber amplifier, which is this one, and our OSC channels. We are going to introduce it in the with the help of this card, and the third one is photo detectors. So these are the hardware components which are used in this card. With the help of photo detector, we are just fetching some kind of power for the control mechanism. And the other components which are used here is power supply. This is basically electrical power supply which we gives to this card. And the processor module is for controlling the gain and to analyzing these power which we are fetching at a different point, and to control the gain of uh, the EDFA through the pump laser. So here this is, as I said, this is bidirectional. So two directions are compensated or processed with the help of a single card. Here the lower four ports are used for one direction, which is the signal coming from side 2 to side 1. Whereas the upper four directions are for the signal which is going from side 1 to side 2. Oh, the EDFA used for the upper uh, direction, which is from site 1 to site 2, this one, it is known as a booster. And whereas the lower EDFA is known as pre-amplifier here. So here we can see we want to increase the gain of input signal which is going in this amplifier. uh, this is coming from the port 6, and this port 6 is connected to your WSS in the system. And this particular PD is for detecting the power in before going to an EDFA. And after amplification, we again fetch the power to see how much is the power out. And we merge the OSC channel, which is a supervisory channel for management of the site at layer 0, just as we have a GCC bytes or some other bytes in SDH, or GCC is in OTN. So it is similarly giving us the management information uh, of uh, uh, of other sites, or we can process that to get the management information. So this OSC byte of this particular site 1 is getting added or coupled with our C band signal at this point. And this is our monitoring port. We can connect the OSA at this point to diagnose the different levels of signal in the C band, or to diagnose a problem, or to monitor the performance of this particular EDFA in more detailed way. And after combining the OSC, the combined signal, which is our C band signal and the OSC signal, goes to line B out. And with this port, our actual fiber is connected, which is going from site 1 to site 2. The same thing is happening in downward ports. Just it's a pre-amplifier which improve your receiver sensitivity of the signal. And here we are getting the signal at port number 8, line A in. So here the signal is combination of our OSC plus our C band channels. So now with the help of splitter, we are splitting the OSC here, and we, before amplification, we are giving the OSC signal or the management information of that particular site to our processor from here, from port number 4. Whereas we have PD also, photo detectors, to monitor the OSC power which we are getting here, and to monitor the input power before giving the signal to EDFA. So once the signal is amplified with the EDFA, again we monitor the power, and we tab the power input and give it to monitor a port, port number 2. Here we can connect the OSA same as we can do at port number 1 to monitor the signal performance of this direction, the signal coming from the site 2 to site 1. And after that, this line A out is there, port number 7. So this line A out is for your is connected to your WSS cards further forward. And we have some refractive events which at the output of the amplifier, which is port number 5 and port number 7, which we try to reduce by increasing the coupling efficiency or a connector at these ports. So these are the ports on the EDFA, and how these work in conjunction. So I hope you understood a little bit more about the EDFA functionality, and I request you to please share your feedback through comments for my improvement. Thank you all for giving your time.